This is it. Some might even call it the most elegant way of finding the volumes of a region that are rotated about an axis. The shell method. That's right. So it's going to be a little bit of a different take than what we learned last time about rotating about an axis in the disk method. So let's go over that really quickly here. So from what we know, a disk was going to be taking any sort of cylindrical disk, of course, with a certain radius, and then you're gonna find it across a different height as it is rotated about any sort of axis and integrating it so you can add up all of the disks throughout that region. Now, on the other hand though, we can then instead call it a shell instead. So instead of trying to find the volume of each individual disk, as you can see here, we're doing 2 pi r multiplied by h. What is that? Well, think of it like we have a cylinder, but this time instead of finding its volume, we are actually just trying to find that outermost area of the shell in that infinitesimally thin wall there. Again, because with any sort of shell, again, if we're just finding just the 2 pi r, which is going to be the circumference of the circle, that means you're just finding that outermost layer, and then you're going to be going across the height. And of course, through integration, we're going to go through every layer of that shell as we fill up the volume of the region. Now, this could be used at times because some might call it a bit more intricate or an even easier way of visualizing how these volumes can come about. So let's try to see what that equation will look like for us if we were to go across an entire region, as what many problems on the exam will ask for. So to begin here, instead of realizing that we're not dealing with just one volume, of course, the volume instead is going to be integrated all the way across from the two limits from A to B. But then, of course, with the 2 pi being just a coefficient, that can just be sitting outside of there. And then if we multiply by r times h, so again, we're doing a two-dimensional area going across, right? Because it's simply just the outermost area in only 2 dimensions right now. But we could bring it to the third dimension of a volume by integrating it along any sort of variable, in many cases, usually in terms of x, as these functions can be described as being rotated across like a vertical line or vertical axis. We'll get to some different examples on that in a little bit. But first, this is going to be the way that these volumes will be found. Oh, no. Oh. This looks even crazier than what we had before, right? Like for many students, yes, it might make more sense. Let's just make a disk. I know what a volume of a cylinder is, pretty easy. But there will be times where a shell method might be actually the simpler option, and for most cases will be the easier option to visualize as to which direction you are rotating in order to find that volume. So why don't we try to see it this way? Because we have the rotation of a two-dimensional object, so let's quickly look at an example over here. So let's say we have some sort of region, let's call it R right there, that we want to find a rotation for. But if we think about it this way, if it's rotated about the y-axis, if we were doing this with a disk method, you would actually need to find those areas then, again, that radius that we're looking for, but that will actually be done horizontally, and then we have to go across the y-axis, meaning that we need everything in terms of dy for a disk, right? Again, that's the idea. Even though you're rotating horizontally, because we're going by disk method, the radius is going to be extended horizontally, meaning we need everything in terms of dy. That will not be the case for shell. In any case, though, the way the shell is going to work is that you are still going to take the actual segments, again, this time going vertically because we're matching it parallel to the axis of rotation, that when it is rotated about, again, we can make those shells, as you can see, right? Everything is going to be hollow underneath it, but that is fine with us because we are just taking the outermost layer, but integrating it across the entire limits of going from A to B for this type of function. So because of that, in the shell method, we will actually use dx for the shell method. Again, the idea being that it's going to be parallel to the axis of rotation. So for those who might know already that they would be a little bit tedious sometimes if all of our functions were in terms of x, but then it turns out the disk method will require the dy integrand, while on the other side, if we did the shell method, we can leave everything in terms of dx, but we just need to find the two different functions that will require us to find the radius and the height of that area which is enclosed, which will be rotated.
Shall we do it?
Let's get to an example really quickly as to see what can happen. Wait a minute. This is the exact same example as yesterday. Yes, it is. This time we are going to use the shell method to find the same exact volume, and usually it will be up to the student to decide whether they want to use either method depending what they find as easier. To take a note here is that the AP exam will not tell you exactly which method to use to find the volume, so long as you show all of your work and get the right answer. So with this, we are just here to present that this works as well for the shell method, and you'll be getting the same answer. It really is just up to the user to decide how easy they want to make their lives to be. So to begin here, let's read this problem once more, that we are trying to find the volume of a solid generated when the region bounded by y is equal to x squared, x is equal to 2, and y is equal to 0. So again, this entire region, all right here, will then be rotated about the x is equal to 2 line. Okay, so it's going to be a horizontal rotation across a vertical line. And so with that, just as a note, again, our volume is going to be defined as 2 pi weighting on the outside, now multiplied by the integral going from a to b of the radius times the height dx. Okay, this is the generic form of finding any sort of shell for this type of volume. And now we must then decide, well, what is the radius and what is the height? Okay, so if you think about it as such, again, the radius is going to be, if you think about it, right, it's how far away our line is going to be across each way that we're integrating. So don't exactly think of it as just the actual function itself, because we're not going by the function. Remember, we're going by dx. We're not looking for horizontal length in terms of x, but we are looking at it in terms of how far the actual limits going from a to b. Again, how long we're going to make this shell go. And that's going to be defined as the radius, of course. Again, how far away each shell is from the center. You can imagine this as the center of the rotation, going all the way around in circles as we continue to go from one end to the other. So with that, the radius then, if we can define it, is going to be that distance from the center. Again, with that center already being a full 2 length away if we started at the very bottom at where point A is. Again, that's the beginning of our integration. So again, think about this, right? We go from the center all the way to the starting point. That means we must have a radius of 2 going. But as we continue to climb across, going from the limit from A all the way to B, that radius will then decrease as we move closer, again, reaching all the way to 0, depending where the x is along that graph. So with the radius of 2 minus x, remember being that you will start at 2 for the full radius, again, if x was equal to 0, but moving as we go across each different layer of the shell, we end up with an x being equal to 2, giving us no radius once we reach the very top at the limit of b. So with 2 minus x being there, and that does make sense as the radius will decrease as we move across the x-axis, but then we must then determine what the height is for this type of shell. And of course, with the height, we are moving up across with each individual part of the limit. Again, that's going to be how high each shell is going to be as it gets rotated across. And that is simply going to be the actual function itself of y is equal to x squared. Okay, so with that, with the height of x squared, it looks like we have everything we need to put all of this together. So from there, we can then construct our actual integral here, leaving the same 2 pi on the outside. The integral now with the limits going from 0 to 2, where this guy starts and finishes. And then we will start submitting in the radius of 2 minus x multiplied by the height of x squared dx. Okay, now this is obviously something that we can very easily integrate here. So let's try to see if we can get around that. We leave the 2 pi on the outside, and then we will then have the integral still actually, because we want to distribute out that x squared. So it becomes 2x squared minus x to the third power dx. And so from here, let's just go ahead and make sure we are on the same page about the way that we set up these types of shell volumes. For one, we have the radius of the 2 minus x. Again, that's going to be the distance from the actual center and then all the way to each edge. But again, of course, that changes along with each passing x. But remember, we start at the limit of a and we end at the limit of b. So because of that, again, we need to start at 2, subtracting the x as we go up. And then the x squared is just the actual height of each point across the limit, making it x squared. So that is how we set up for each of those parts. And then we can run the integration. So going from there, the 2 pi will remain. We end with an actual integration of 2/3 x to the third power minus x to the fourth over 4. And then we are evaluating this from 0 all the way to positive 2. Okay, so from there we can go ahead and just run this last bit of analysis, and we should hopefully end with the same exact answer as we did last time. So with that, the 2 pi will remain. We end up with the 2 being plugged in, so it's 2/3 multiplied by an 8 minus a 16 over 4 as a result of this type of integration. And then we subtract the 0 because the lower limit of 0 will just cancel out with all the x's there. And so with that, we can then actually distribute the 2 pi across both of these guys because the over 4 can be simplified a little bit there. And so because of that, we end up with a 32 over 3 pi subtracted by a 16 over 2 pi. Okay, with a very nice and easy distribution right there. And because of that, we can then go ahead and make the common denominator of 6, giving us a 64 over 6 pi subtracted now by a 48 over 6 pi, leaving us with the final fraction of a nice 16 pi over 6, with the simplification of going 8 pi over 3. Okay, and would you look at that, if we were to check yesterday's video, that is, for the same type of problem, we do end up with exactly the same volume that we should have, with the same kind of rotation, with the same function.
Isn't it wonderful?
I think it is. That now we have students that can use both methods of finding these types of volumes, and there should be no problem for us answering whichever difficulty of problem there is as you move across these different problems. So with that, we should be good to go to actually get to some example problems tomorrow using both the shell and disk methods. Remember, there are 2 different formulas which need to be memorized. The AP test will not give you any of them. But even with that, we should be well equipped to move on to some real problems, and we'll see you there next time.